Here we have a difficult problem. A hollow sphere is rolling down a ramp, and we want to determine the acceleration of the sphere as it rolls without slipping down the ramp. And we're given a little help. They tell us the answer should come out to 3/5 g sine theta. So how do we go about this? Well, with acceleration, we want to think maybe about Newton's laws. So let's draw a free body diagram of a rolling object. And so you draw it big, don't draw a tiny little circle. And I like to indicate the center and then the contact point with the ramp, which would be offset to the right a little bit. And that can help draw the forces. We need to draw them where they're applied. And so gravity, mg, acts at the center of mass of the object. And so it's kind of the average location of the weight of all the atoms in the object, right in the middle. And then we have the normal force, which acts here at the contact point, and it goes right up through the center. Something like that. Maybe you could do better, but that is the normal force. And then without friction, this thing would just slide down the ramp, so we know there's got to be friction. And it's static friction since it's rolling without slipping. And static friction is up the ramp and parallel to it, opposing the motion. And so static friction is that. And now we need to pick a point to apply Newton's laws of rotation to. And we can either sum the torques about the center or the contact point. And so let's try the contact point since that's a little unusual. And so I'm going to say the sum of the torques about the contact point is what's controlling the motion of this object. And so what forces have torques? And so we need sum of the torques. Well, torque is the force times the lever arm. And the lever arm is the distance from where the force is applied to the rotation axis. So let's take a look at the normal force. And so the normal force is applied here, and that's the rotation axis, so no torque from the normal force. How about friction? Friction is applied here, and that's the rotation axis, no torque from friction about the contact point. How about the weight? Definitely part of the weight is applying a torque. And so the distance from where the weight is applied to the contact point is the radius of the object, so that's my lever arm. But the weight is not perpendicular to the radius. And so we want the perpendicular component. If this is angle theta here, this is theta here. And so the component of the weight that is causing a torque would be the opposite side, or mg sine theta. And then don't forget the lever arm. So torque is the force, or the component of the force perpendicular to the lever arm, times the lever arm. And so that was tough just to get the torque. Now we need to get the rotational inertia, and if we're rotating about the contact point, or at least imagining that's what's happening, we need the parallel axis theorem. And so the parallel axis theorem says the rotational inertia is that about the center, plus a correction term, mh squared. The rotational inertia about the center would be given to you if this was on the AP test, 2/3 mr squared, and then the correction term, h, is the distance from the center of the object to the rotation axis. And so h equals r in this case, and so the correction term is mr squared, and so that's 3/3 mr squared plus 2/3, so we get 5/3. So we can put that into here for the rotational inertia. Now I want the linear acceleration, not the angular acceleration, and so there's a relationship between those two that you should know. The linear acceleration is the angular acceleration times the radius, and so the angular acceleration is the linear acceleration over the radius. So we can substitute that into there, and we're left with this mess. But look, there's some simplification. I can cancel out that r. I can divide both sides by r, and I can divide both sides by m. And so if I solve that for A, we're done. 3/5 g sine theta. How about that? This takes practice to learn this. This is one of the hardest things to do to get ready for the AP Physics Mechanics C test. And so if you want to be ready, try summing the torques about the center and see if you can show the same result. If you have trouble, watch the next rolling acceleration video.